Let's talk about fluid flow, either through pipes or just in the airstream, say, like eventually how airplanes fly. So I'm going to imagine a pipe as my initial scenario to be able to illustrate. I've drawn a picture here of a pipe that narrows as it goes on. And something interesting happens in a pipe when it narrows. The first thing we want to talk about is continuity. The continuity principle considers a pipe, and what's important to note going into this is that the fluid that enters the pipe has to exit the pipe. I mean, duh, right? That kind of makes sense. But what's really interesting here is we're talking about volume flow. The speed of the fluid's not going to wind up staying the same, and let's look into that a little more. So how does the speed of a fluid change as the pipe narrows? Once we stipulate that the fluid flowing in equals the fluid flowing out by volume, we're going to define a new type of rate called volumetric flow. The volumetric flow rate, Q, is the volume per unit time. It's usually measured in something like liters per minute, gallons per hour, right? A unit of volume divided by a unit of time. So one note here that I've put off to the side is I need to make sure that you are drawing a V for volume differently than a V for velocity. What I'm doing is I'm putting little capital letter serifs on the V for volume, and when I write velocity later on, it's going to have this little like tail on it. They're going to show up a lot in this stuff together, commingled. Got to keep them straight so you know what's what. Considering a volume of a circular section of fluid, I've drawn here the face of this circular section has area A and depth D. This is like a chunk of water out of that pipe. The volume of that fluid is area times depth, right? It's a cylinder. That's how that works. You find the area of one face and the depth. So I'm going to replace volume with area times depth over time. So this equation gets rewritten this way. Now, it turns out that that D and that T, that's a useful quantity for me. So I'm going to rearrange the equation just slightly, and I'm going to write it this way. I'm just bringing the D and the T a little closer together. They're buddies. They want to hang out. Because when we have a constant fluid speed through the pipe, it's another stipulation here, velocity is change in position over change in time, or sometimes written D over T. So another way to write volumetric flow is substituting out D and T, D over T, to be velocity. That means the volumetric flow in a pipe can be expressed two different ways. Here, we'll write that down so we've got it. Volumetric flow is either volume over time or area of the pipe times the velocity of the fluid flowing through the pipe. There's an interesting relationship I've written here as a therefore statement. This means that the speed of the fluid in the pipe increases whenever the area of the pipe decreases, and you hold Q constant. So remember we started this discussion with we're going to assume that the volume of fluid flowing in equals the volume flowing out. In this picture, I've got a pipe that gets narrower. Cross-sectional area gets smaller. That means the velocity of the fluid has to go up because volumetric flow equals area times velocity. If one goes up, the other's got to go down. Maintain a constant product. Thank you for studying with me about fluid flow, the continuity principle. Good luck problem solving.